Everyone, this is Code and Code and Deploy. So thank you so much for being here. And my name is Ezequiel Lanza. I am here, Ezequiel Lanza. I am an AI open source AI evangelist, and I work for Intel and our team open at Intel. And basically, what we want to do is a coding session. So we would like to share with you some coding sessions. We like to work for developers, and we would like to code something and to build something really from scratch. So it's our first time doing this live streaming on both channels. We are streaming on LinkedIn and YouTube. So please let us know if in the comments if everything is going well, if the audio is great. Also, write me. We would like to know from where you're watching from. We would like to know if we have people from the entire world of where you are watching us. So we will wait a few minutes to give more people to join. But before that, I would like to make a quick introduction about what we will be doing. It's a code and deploy. Is the name. It's a coding session. It's a show for developers because this is how we learn, right? So we start coding, and it's okay with the slides. It's okay with show everything, but we need to put our hands on. And this is mainly the idea of this show. We would like to invite community leader, community experts, so they can come here and they can code with us and to prepare something. So let me know if everything is going well. I will be introducing my first guest, which will be coding something for us today. We'll be deploying something, and his name is William. Hi, William. His name is William. Here we go. Hi, William. How are you?
Good. Hello. Can you hear me well?
Yes, I can hear you perfectly. So just let me know, the audience, if everything is going well. So we are live. So thank you, William, for being here. We really appreciate to have you here. I was saying that we will give some minutes to allow some people to join. But before that, just tell me who you are. Tell me your background, and tell me that you're working for a company. So tell me a bit about yourself.
Thank you, Ezequiel, for the invitation as well. So I am a developer advocate at GitLab. And one of the things that I enjoy the most is that for at least 8 years ago, I started learning machine learning from the very beginning, from scratch, when it can be scary, when you start learning to define a classifier for every X, such that, and just looking at the math equations and deriving everything and all of these things. And I am very impressed with how this field has advanced and all the number of abstractions that we have today. So big part of my time these days is taking all those fundamentals that at some point I went through from the academia perspective, building solutions and POCs that are tailored to solve problems from real life or just problems that I want to solve for fun. And this journey brought me to the point that I started learning DevOps like 4 or 5 years ago. And I found that it was incredibly helpful for the things that many people do when it comes to develop machine learning models. And back in the day, like 4 or 5 years ago, when I started learning this, I realized that, okay, at some point we will be talking about how can we, there will be a new name for these things, like in the tech industry that they like to put new names to everything. And today, fast forward 5 years, we have the MLOps term that has been coined like that. And one of the things that I want to show today is the expertise I have been building inside GitLab when we take models and we put them into production environments by using CI/CD principles that we borrow from software engineering.
Nice. So you mainly started working before ChatGPT, mainly.
Yeah.
Because we
Yes,
always say,
way
right? So
before.
most people started after ChatGPT, and most people started before ChatGPT as us. So okay, nice, great. So yeah, let's go and start coding. Let's start doing something. Just let me.
Okay, so yeah. So today we will combine two things. We will combine a very funny problem, which is there are tons of pictures of cats, data sets of cats on the internet. And I'm sure that everyone who is a pet lover, they have a lot of pictures of their pets in their phone. So I was thinking that it would be great that instead of doing the traditional dog versus cat classifier, I want to take pictures, the hundreds or thousands of pictures that I have of my cat in my phone, on my phone, and then train a model and see if it's able to recognize my cat amongst other cats. I was just exploring that idea because you can if when you see two cats and this cat is different, it's because there are certain features of that cat that you can use to classify. So I say, okay, it would be great to test one of these models from scratch because I wanted to have the feeling of, okay, let's build this layer by layer and let's make some use of the pictures I already have of my cat. And I re-downloaded other open source data sets that are available. And so this is what we'll be building today. It's like, what can you do if you have thousands of pictures of your pet and you would like to combine neural networks, deep learning with that data set and see if you can build a classifier that can recognize your own cat. Yeah. Yeah. So moving forward, a little bit of formalism and in the explanation. So what is the task? We have a data set, traditional machine learning workflow. We have a training data set and a test data set. In the training data set, we have pictures of cats. They are labeled, and the label is, this is Meowski and no Meowski. Meowski is the name of my cat. So this is what will serve as the label. Yeah. So these are the way that this is a supervised learning problem where we have images and a label. The label that we want to learn to classify is Meowski. So what are the tools or the tooling that we'll be using here? All of this is the big chunk of this is open source, which is I'm going to be using PyTorch to build the neural network, MLFlow to track the experiments that I will be doing. I will show you how this works, and another library that is very helpful to build user interfaces for these machine learning models to test them or to give a sense to other people if they want to try. This has been very useful in my workflow at work as well, because if you recall, if you have been, as we were saying before ChatGPT, many things that they look great in Jupyter Notebook, then you want to show it to someone else. And if you say, let me show you this model, and then you show them this environment with cells and everything, and say, if you run this, look at what I did. So what we'll be doing is that taking that Jupyter Notebook and changing it in a way to refactoring, so I can deploy it in a container and serve it with a UI. So I can play with it, trying different pictures, let's say in a almost production-ready environment deployed to the cloud. And all of these tools and technologies are going to be orchestrated by GitLab using CI/CD principles and developer workflows to automate big part of what we'll be doing, from creating the model to training the model and then deploying it to the cloud.
Nice. It's more like an end-to-end. So it's a typical workflow, right? As you said, we always start like we do the Jupyter Notebook, and they give you the Jupyter Notebook, and they say, okay, go and deploy it. I have no idea how to do it because I just have the Jupyter Notebook, right?
Yeah.
But that's very useful. Yeah, great.
Yeah, that was the main inspiration when I started learning DevOps. That there were two
The
main things
frustration,
that,
let's say, right?
yeah, it was an inspiration out of need. That many times I wanted to share something with someone else that wasn't close to my computer. And when I was only machine learning, this concept of, put this thing in a Docker container and deploy it to a Kubernetes cluster, create a API endpoint and all of these things where you knew those words, but they were not necessarily internalized in the workflow because you are more focused on trying different architectures of models. So this is one of the things that was really good when I started learning DevOps with GitLab, is that everything is there. So you have the repo, you can connect the repo to the CI/CD pipeline. When you make a commit, you can automate what do you do with this code and where can you put it. And this could be different environments. You can pull containers, you can deploy to different endpoints and targets. So this was the one of the main things. And the second is that machine learning is very experiment oriented. You have to iterate a lot. You tweak something and then you have to run again the experiment. You tweak another thing, or there are lots of changes in the hyperparameters that you can try. So these have a lot of manual steps. And after you do it for a certain amount of time, you say, there must be a better way, more efficient to do this. And this is when I discovered that there are the principles of continuous integration and how you can automate many of these commands. And you just focus on doing something in the code, commit, add, commit, push, and then all of these things that I used to do by hand on the terminal, they will be done automatically somewhere else. And I just worry about the output.
Great. Amazing.
Okay, so just a little bit of theory. What we'll be building is because it's an image or images that we have. So what we want to do is to use a convolutional neural network with max pooling layers to extract features from the image. As you mentioned in the beginning, this could be kind of tricky because there are cats that they have similar colors. So I try different architectures and hyperparameters to be able to extract as much as possible features that make Meowski and be able to differentiate between two cats, especially when they are tuxedo cats that they have the same colors. So now let's move to the actual coding. So is this okay? The zoom of the screen here?
I think it looks great for me. Just let me know what the audience says. But it looks great to me. So let's move on that. And unless someone is not able to see it, but let's keep doing that. Yeah.
Okay. So I will just make a quick review of the imports that we are doing here. I will just FYI, I will make available this notebook and the project, everything. So if later someone wants to review the recording and look at the code base or the repo, they can fork it or they can use it. So main things here to highlight is that, as I mentioned at the beginning, we are using PyTorch. So I am importing all the things, the minimum thing, the basic things that I need to start working on this. So I'm importing the neural network module to create neural networks, to add activation functions, and so on. We need a library for datasets because in PyTorch, a good practice is that you decouple from the data from the modeling. So there are different ways. There is this way in which you can have a dataset object that is separated from the modeling part. And the transforms library, because we have to, I will explain this in the code, we have to transform the images that we are feeding into that we want to feed into the neural network before we actually feed it. And the good old matplotlib to do some visualizations. Yep. So we start with loading. Step one, there is no machine learning if we don't have data. So we start by using one path object to load where I have my dataset. So I have my dataset located here in this in my local host in this folder. So with this, what I'm doing is that I'm creating a data set. I am giving the path of where I have the data set. And here, this is another, the second part. So once we define where we have the data set, now I want to define what are those transformations that I want to apply to the images that are part of the data set. So here, these numbers that you see here, these are numbers that I calculated specifically for my data set. Usually, if you go to do normalization, usually if you read examples online, they will use certain numbers that are calculated from the ImageNet dataset. So because my dataset is very small and is not contained in the ImageNet open source dataset, so I decided that it was a good practice to calculate the mean and the standard deviation per channel of my dataset to apply normalization to it. Just because this is a dataset that I'm just starting to study, let's say, the one that has my cat pictures. So that we import the transforms library. So now we start here saying that I want to create, this is pretty cool because what this allows me to do with using this compose function is that I can chain different steps that I want to apply to the batches or to the images. So by using this compose function, I'm going to start telling it, so we will do this in this order, in this sequential order. So the first thing that I want to do is that I want to use the resize function, because recall that we have pictures that are in my phone, that they were in my phone, that they can have different dimensions.
Sizes, okay, dimension.
Yeah,
so you're trying
exactly.
to find the same dimension to all the images.
Yes. So I am taking all of them. This transformation will take all of them and will pass them through a resize step that will make them all 224 by 224. And also, as we were mentioning in the beginning, there is this challenge that when you have a small data set, deep learning in general, neural networks that have deep convolutional layers, they are hungry for data. So one of the things that you can do when you don't have that much data is to apply data augmentation. So here I'm going to use this another function that is called random rotation. That what I'm doing here is that each one of the batches of the images, or each image that I am feeding to this transforms function, is going to be rotated 30 degrees. The idea of this is to help the algorithm to generalize better, to not overfeed, always seeing the same, like say, perfect shot by feeding it in different angles.
But you are rotating the same image, or you are generating new images rotated?
No, I am rotating the same images every time that I load in the batch. Yeah.
Okay.
And now this is very self-explanatory here. That the third thing that I want to do is that I want to convert this image data structure into another data structure, which is a tensor. This is what let's say the fundamental unit of all the calculations when we are doing training neural networks. That's why TensorFlow is called like that, because you define a lot of layers and you have a tensor flowing through those layers. So that's a very good name, TensorFlow. So in this case, we are using PyTorch, but you get the idea. So we are taking that and now, yes. So now we are converting it to tensor, because this is the data structure that we need to perform all those operations that we want to do on the images. Lastly, as I mentioned, I will take the last step will be to normalize the input data. And here I'm going to do a quick hack of doing that. What I need to do, this normalize needs a mean. And let's call it mean equals mean, and it means standard deviation. Yeah, so what I'm doing here is, as mentioned, I took my own calculations to normalize the images. And this is a very important step in neural networks. There are hundreds of papers that explain what is the effect of this, but without loss of generality, we are doing this to keep the values of the pixels in some range. And by having it there, we can also speed up the convergence of the neural network. And when I mean convergence is that we will see this in the training step. We will train a model, and this means that it will be doing a lot of matrix multiplications, and it will be optimizing a function. And when we have this normalized, we are helping the neural network to converge faster to that value. That is the one that we needed, that will give us the hyperparameters the ideal hyperparameters that we find. So far, so good. Do you have any question?
Great.
Good.
I don't know if the audience has any questions. From my side, everything great, clear. Yep.
Okay, cool. So now that we define the transformations that we want to apply to the images, now we want to create the dataset. So in PyTorch, the dataset stores the images, and it has a lot of, I don't know if a lot is the word, but it has certain functions like this one that is called image folder. That is pretty helpful when you have a dataset that is structured in the way that I have mine. So let me show what do I mean by that. So when I go here to this folder data, you see that in training dataset, I have one folder that is called Miowski and another folder is called no Miowski. This is when we use this function image folder, what we will be doing is that it takes advantage of that structure in the folder and will assign a label to each one of the images that are inside certain folder. And this function needs then some parameters such as root, and the argument that we will be giving is the dataset folder. Did I call it dataset folder? Yes. And the second thing that it needs is the transforms. So, and the transforms is called transforms, which is what we define above. So doing this, did I import this? Okay, help me here to did you see the error?
Datasets. Yeah, datasets.
Datasets, and now we have a second error. What is it? This is very cool. You can help me.
That's why it's a coding session. That's the fun part.
I see it. It's because usually when I do this, I am quiet and I am saying things and then I'm writing. So I was saying that we define transforms. So I was passing this as transforms, but the actual parameter is called transform, not plural. So that I removed it, so it went through. And so now this is also another PyTorch foundations, which is one thing is having the dataset where you store your data, in this case, our cat pictures. And another thing that we need is a way to iterate over this dataset. So there is another function, another class that we imported here that is called data loader, that once we have a dataset defined, now we need to create a data loader to be able to iterate over those images and also create batches of it. Because remember that not everyone, especially when you're working offline, you have computers with a lot of gigabytes of RAM. Yeah. About the things that is needed to do is that you process the images in different batches so they can fit in memory. You don't feed the whole data set at once unless you have, usually it's not a good practice, but if you don't do this and you are working in a consumer machine, you might hit a limit that your RAM is telling you, sorry, but it will break.
Yeah.
Jupyter will
explode.
Yeah. So this data loader needs a data set, which we define above in cell number 9. And it needs, what else do you think it needs? Okay, it needs the batch size, what I was mentioning about not having enough memory. And I want to add this parameter that is called shuffle, that every time that I load a batch, it will shuffle the images.
The images, so not to train with the same image, just to try to generalize.
Yeah. So far, just to do a little recap, we did define the transformations that we want to apply to the images. We created a dataset object, and now we are creating a data loader to iterate over that dataset. And we defined that we want to do it using batches of 32 images per batch. So this is what I define in this line of code here. Now I'm going to apply it. So it's a very good practice, and this is usually where people spend a lot of time, because it's also fun, which is inspecting the data.
Yeah.
So here on this step, since I already have the training data loader object, what I want to do now is to select some samples from it. So I want to select one training image with its corresponding training label. So let's do that. So now I'm going to select just from training image. I'm going to select the first. So I put this index here. I want a label, and it's called training label. I want to select the first label. This line here was one of the pitfalls that I once fell into, which for that I have, in case that people don't know, or if you are watching this later and you don't understand why I have this here, I have a slide for that to explain to you why is this. So we are working with tensors. You remember that one of the transformations was to convert the data image to a tensor. Mm-hmm. And the tensors in PyTorch, they are defined like this. The first is the channels, then we have the height and the width. But we want to plot one sample of the image. And for matplotlib, this library says, I first need you to give me the height, then the width, and then the channels. So because you see that there is a discrepancy between how it is structured in PyTorch and how matplotlib needs it, we use this function, this method permute from the tensors that allow us to switch those the height, putting it in the index 0 and so on. And when we do this, we get the height, width, and channels the way that matplotlib needs it.
And of course, the height, the dimensions, in the vector you have the dimensions, and you also have the channels. Mm-hmm. What are the channels, or what will be the channels for that image?
Yeah, so because I have pictures or images here that they have the color, the RGB channels, there are 3, and I have all of them because they are color image. So the channels are this number that in our case, this is one way in which you describe an image using because you can make any image by putting all these channels together, the RGB channels. And these images being color channels means equals to 3 because they have because they have
different colors.
Yeah. They are not like the traditional, this data set that everyone, the hello world from machine learning, the MNIST, the one with the numbers. This is black and white. You don't need the 3 channels, just one. So now that we do that, you see that I am iterating on the data loader. And here we see that, for example, this picture of this cat here, which if you don't know my cat, you might think that is my cat because it's tuxedo 1. We see that it has associated a label 1. So this is a Nomiowski. And this one, I know this is my cat, is label 0. Okay. And this is again my cat, label 0. So far we have learned that by using the image folder and having this structure, the Miowski got the label 0 associated to it. So now we have numbers. As you know that when we are doing machine learning, we are working with numbers and optimizing matrices with linear algebra. And now we have a number that we can plug into all of these machinery and equations. Is that so far so good?
Yeah. So we'll have a bunch of numbers from one side, matrix and everything representing the image, and we have a label. And that will be what will be training the model.
Exactly.
Nice.
So good. So now we start the process, the modeling process. And I just want to emphasize that it's very important to spend plenty of time in massaging your data set and getting to know your data set to do more things. This part is also is the sexiest one when we do the modeling. So this what I'm going to do here. This is in the documentation of PyTorch. This is a very standard expression. That what we are going to do is that we said I want to use a certain device to do all the training. So if I happen to have a GPU, I want that the PyTorch will automatically put the workload into the GPU. So we say that you should select CUDA if torch the CUDA, I don't remember, yes, CUDA is available. So if this evaluates to true, you should load the tensors into the GPU that you have available. If not, or else, we want to use this backend that is called MPS. Are you familiar with what is this MPS?
No, I'm not.
Okay, so I will write this and I will tell you. So here, what I'm saying now is that I'm asking Torch backends and MPS is available. So some Mac, the M1s, I think, from M series, they have GPU. And PyTorch says, if you have this Mac, I can offload part of the training to the GPU of your Mac.
Okay.
So if, like in my case, I have one that has is compatible with this backend, the training will be done there. So if Torch backend's MP is available, and if none of the previous ones, so what we do is that we want to put this on the CPU. And if you hit the CPU and you do this with CPU, so depends on your hardware. But yeah, so we see here that also this is very important to do around this device, because you will see that when we when we go from the Jupyter Notebook to the actual refactoring and we push it to the repo and we run CI, one of the runners, they are GPU enabled. So I want these things to be able to detect that the script is running in a different backend. Yeah, different hardware. So now here, I just put the skeleton of what is one of the funniest parts. If you really want to grasp and understand all the things that are going on when you use facial recognition or when you see how your different things that can be classified online using images and so on. This is where big part, I mean, this was what was very funny for me in some years ago to build the neural networks and try things with them, try different architectures and just see what happens and what will work. Sometimes you add a lot of things and you think that because you added more things, this will be more powerful and you start overfitting or the algorithm doesn't learn.
Yeah, that's a typical mistake, right? We would like to do something really cool, really advanced, but you probably don't need it. Yeah.
Yeah, so here, this is a PyTorch kind of template that you have to define a class and you have to inherit from this module that we imported in the beginning, the neural network NNN module. This will provide you with the different activation functions and layers of neural networks that you need to build any architecture that you want. So in the ABC of neural networks, is well known that when you have images, you want to use convolutional neural networks, and because it's an image in X and Y, we want to use the 2D. And here, to your question of the channels, so because we have a color, the input channel will be 3. It means that we have data with 3 channels. And I want to generate 32 filters outside, and then explain what is this. And I want to pass it with a kernel size of 3. Padding equals 1. So here, I just trying to make my life easier. I selected certain hyperparameters that I know in advance that they will take the image. They will start sweeping over the image with this 3x3 kernel size. In some literature, is called a filter. I don't know if there is another name for this filter kernel size. That what it does is that you have the image and you start sweeping through it, doing matrix multiplications and extracting features. So this is basically a layer where, to that question that we had in the beginning of, I have different pictures of cats. What makes my cat? What makes Meowski a Meowski? This is the layer where we will be extracting from all those images and learning what are those characteristic features that make a Miowski, and not other gray cat or another cat. I actually do a label, I put it like other gray cat because all cats are great. So this is the main template. So we usually have to put an activation function. This case, the ReLU after the convolutional layer, and this one, which will help me to reduce the size of the image and make computation faster, and also extract the most significant features that the kernel, when it was sweeping through the image, was able to detect. So also, just for simplicity, I am putting it as 2, because you will see why I am labeling that this max pool will be of 2 by 2. So here, till this point, what we have is one layer that is very, one layer, no, this part. We have a convolution, activation function here, and then max pooling from this neural network. We want to use more layers because it requires more layers to extract more features. So I'm going to do a quick thing here, which is I'm just going to copy because it's the same. And here you have to pay attention to the input and output channels. So in the previous layer, our output channel, the number was 32. So this 32 is what enters in the next layer. So what is the output of the other one becomes the input of the next layer. And then I want that at the output, I want 64 features, and I keep the other things the same. So now that I put this here, let's add 4 convolutional layers. So I want to add another one. Same story. I say that the input is 64 and the output will be 128. And then I will finish with the last layer that I want it to be 200. Where is it? 256. So input channel 128. And output channel 256. Remove this comma.
And this is something that you define based on testing.
Yes, but there are, initially, yes, but also there are lots of papers and inspirations where they show you this particular architecture with these particular hyperparameters work great with this type of input data. So I took just the traditional one, and I added one more layer because when I was doing testing, I saw that it wasn't working that well. So I added one more layer to extract more features. So now what we have, and going back to this, is that we define the convolutional layers. And usually in a classification problem, then you want to connect the convolution layers. They are there to extract features from your input data, and those features are the ones that will help you learn and minimize the loss function or the cost of the function, meaning the errors that you are having. And then when you have that, you will connect it to a fully connected layer that will do a regular classification problem with, in this case, two outputs. One for a probability that will be, let's say, a vector with 2 dimensions that will contain 2 probabilities, and we will choose the highest probability, and the highest probability will be if it's a Miowski or not Miowski, depending on the labels that we are using. So because I just mentioned that we have a convolutional layer and now a classifier layer, this one is not convolutional anymore. And for this one, we will use another type of layer that's called the linear one. So there is a reason why I also have another slide to show you something. So from the theory from before, you see that the output that we have here is 256. So that output will be the input of this linear layer. And now when I was learning this, that back in the day, there are now ways in which this can be automatically calculated for you. Even in PyTorch, if you come from Keras, I think you never worry about this. Yeah, but what is the numbers that we need to add here so the architecture can fit and can match, and all these matrices multiplications can go on? So I want to highlight that by using this pattern of 1, we are keeping the same size of the image. And we started with an image that is 224 by 224. And we have 4 of these max pool, that this is reducing the size of the image. Mm-hmm. So because I have it 4 times, it means that I will have to divide it per every layer. So this is an example of a picture. Every time that I pass it through a max pooling layer, it is half in the middle. So it goes from 224 to 112, 56, 28, and 14 by 14. So at this point where we are now in the neural network, we don't have any more the 200 by 24 image, but we have a 14 by 14, a smaller one. So we have to account for that to make this neural network be able to multiply. So you see that I am saying the output channel, and here there is an error. This has to be multiplied because now when I linear, I will see it as a flat version of it. So I need to account for all the dimensions that it has. So it is the multiplication of the 256 that was the output channel, and the new height and the new width of the image. And now this term is arbitrary. I want to say that this linear layer will have 1024 outputs. And another thing that I didn't mention is that I am using this class sequential that it allows me to do the things that I'm doing, which is stacking layers of the neural network. So now, like in the previous case, it's always good to add an activation function so you can detect nonlinearities in the input data, in the classification problem. And here, this is another layer that we didn't see before so far, which is very interesting. This is relatively new, but you know that in machine learning, every week there is a breakthrough.
There is something new every day,
yeah.
I would say. Yeah.
But I remember when this was the thing. So one of the main problems when in pattern recognition or building in a supervised problem is that you might end up memorizing the data set. Then all these tweaks that you do to the weights and biases of the neural network, they will just adjust to satisfy the structure of your input data. So there was a paper years ago that was describing that using this dropout layer, what we are doing is that whenever I am doing all these mathematical operations, there are components of the tensor that they are carrying information about the features that it learned, and I am going to zero them. I'm going to make them zero or drop them. That's the name. So when I do this is what is called a regularization technique. What I'm doing is that I am forcing the neural network to not get comfortable saying, oh, I already know this. No, because maybe in another pass, that value will not be there. So it will have to learn. Yeah, it will have to extract patterns from somewhere else. So this number is that it will use, it's a probability number. So it says that it will, out of all of the tensors, there will be 20% probability that some of the feature values will be zeroed, will be go to zero. And now we repeat the second layer, because remember we have here in this other slide 2 fully connected layers. And now we do again linear, and we pass the output of the previous one that was 1024. And now I said that it has to be 512. I am now reducing the size of the neural network. And let's finish by adding I'm missing a comma here. And adding the ReLU, same here, the dropout again, and then the output layer. So
that the output will be 2.
Yeah, exactly. And the output will be 2 because what we want to do here is Minkowski. No, Minkowski. This is the 2 possibilities. So that's why we have 2. So now what we did so far, this was the difficult part, let's say. This is the part that it's very interesting because these days when people usually work with these things, they are using pre-trained models, which is completely valid and is the way to go. You don't start from scratch like the way I'm doing here. But one of the things that I share with my students is that it's very important, at least if you find it intellectually stimulating, to be aware of the fundamentals. Because even if you just want to use pre-trained models, because that's what you should do when you are working, you don't want to reinvent the wheel. But if you are working with pre-trained models, you need to understand at least how they were built and what is the architecture that they have. And to do that, you go to the research paper. And in the research papers about those models or new techniques, they use all this jargon. They don't care if you don't know what is a dropout or what is a vanishing gradient of all these things. So even if
that's great. Yeah, go ahead.
Yeah, so this is why I see that there is a lot of value in understanding how these things happen. Although you could use a retrain model and still fine tuning.
Yeah, but you also would need at least to understand when you are fine tuning or when you're using for your use case, you at least have to understand, because the generic thing is fine to download the pre-train and everything, but when you would like to use for your case with your data, and you need to at least understand what's going on inside. And it applies for convolution for CNNs and applies also for LLMs. So yeah.
Yeah, especially these days.
Especially LLMs, let's say. But the transformer is a bit more complicated, right? But
it is. It is, but I will say that at least if you understand some fundamentals of how the word vectors, the attention scores, and all of those things, you understand that it's not really getting sentient, the model.
Yeah.
You say, how come?
Yeah.
That's a bad joke. So now what we do here is the forward pass. So remember that we are taking images that we convert into tensors. We will extract features, and then we have to do a pass with this data, do all the multiplication of input by weights. And this is the famous forward pass. So in this method here, what I do is that I take the layers that I define, and I will pass the input data through all of those layers. So this is what we are doing here, taking all those images and passing them through all of those convolutional layers. And then this is also kind of boilerplate code that the output of this will be in certain dimensions that are 4D, because that's what the convolutional layers give you. So what you have to do is to flatten this output. So if you come from Keras, you know that there is a very easy one that is just called flatten. And just read the documentation. This is saying that we are flattening this output from the convolutional layers, and we are making it compatible now with what we need to feed into this classifier that is a fully connected one. And so this is the last step. So here we do the self. Now so I pass it to the layers. Now it's flattened, and now I need to take this flattened version and pass it through the fully connected classifiers. So I have to classifier, and classifier receives the input data X, and it returns X. So this function
I really like from PyTorch. Compare with Keras when you don't have this forward function. I mean, it's nice that in PyTorch you have that you can do some stuff there. You can configure that part. In Keras you don't have that ability. I mean, you can do something, but with this function, I mean, I really like PyTorch. Not just because of that, right? Because of multiple things, but that thing is it's really great.
Yeah, when I was in the university, I remember that there was a discussion between the industry back in the day and academia. In academia, back in the day, they prefer PyTorch because they said that it was easier to debug. Yeah. That's what they were saying back in the day. I didn't know. I was using TensorFlow and Keras back then. And later, when I started learning PyTorch, because if you really want to grasp and try things as quickly as possible with transformers, to go language, the to-go is PyTorch.
Yeah.
Then you have noticed that most of the are first available as in PyTorch than other frameworks.
Yeah.
So yeah, so here this is the recipe of traditional machine learning. So what we did so far is that we define a class that has the architecture of our neural network. So we have to instantiate it, and this is the typical workflow. So we need a loss function. This is the one that is going to tell me if the classifier is doing a good job. This is or in some other places they call it the cost function, like how costly is whatever you're doing. So you have to correct. So there are different loss functions. And when I use gross entropy loss, that is a good one for these classification problems. And the reason is that in the future, I want to add not only Miowski, the cat that I have here in the Czech Republic, but my parents' cats that are in Colombia. So I want to add more labels to classify. So by using cross entropy loss, I am already leaving open to just change a little bit the architecture and be able to add more categories to the classification problem.
Nice.
Mm-hmm. And then this is also traditional. There is a lot of papers to read about this. Is the optimizer. This is the one that has all the math that you saw in calculus and engineering or last years of high school, depending on your high school, where you were basically doing derivatives, finding gradients. Back in the day, I remember when I was studying that in school, I didn't know how relevant it was going to be later, because you just get used to say, okay, I have this function. If I find the derivative, I am finding the slope of the line that is tangent to it. That's it. Turns out that that's the main thing that we are doing here with the backpropagation algorithm, is taking the derivative of the weights and biases with respect to this loss. And when we do that, we are optimizing. And if we optimize, it means that we are heading towards a convergence point, that it means that the neural network is learning. So there are different optimizers. And this one, Adam, it has a bunch of reasons why is one of the most popular. I invite you to read more about it. I don't want to go into details. But things that I know is that it has momentum, which helps to avoid divergence. And here, so what I'm saying is that I am defining the optimizer and I am passing the parameters of the model, meaning the weights and biases that I need, because this is what we can tweak to learn, and the learning rate that will tell me how the size of these steps that I should give.
We actually had a question that it's why you're not using a function like softmax at the end of the classifier?
Okay, that's a very good question. It is already there in the prediction step. And the tensor that this will give me will be a tensor of 2 dimensions. And then in my prediction step, what I will do is that it's already there. It's already giving me the 2 probabilities that they together should add up to 1. So I don't have, in this case, to explicitly add it. I will show you here when we go into the training loop. So now this is we say. That's a word in Spanish to say that this is more of a transaction here. The interesting part that I want to highlight from the training step is that here is where, if you are paying attention in calculus 1 and calculus 2 and 3, in vectorial calculus, and this is will make a lot of sense, which is one of the things that I advocate to understand at least once, seeing it once, why it happens. So what we are doing here in the training step is that first, it's very important, in PyTorch, you have to tell the model that is in training mode. So we are setting it to train. And why? Because the dropout layers, they behave differently when you are training than when you are testing it. When you are training it, the dropout is happening, for example. So here what we are saying is we are taking images and labels, and we are going to reset the gradient. And now we are going to pass those batches of input images into the model. And this model is the one that we spent some minutes here defining. And now these outputs will give me a prediction, a 0 or a 1. And I want to use the loss function that we define here, cross entropy loss, and calculate that cost, calculate the loss between the prediction, the output of my model, and the ground truth, which are the labels that are part of the training dataset. Then I will find an error, and then I will have to backpropagate that error back to the input. So this is the magic of how neural networks learn. You find an error, and then by using chain rule, you start
another batch, and you keep learning every batch or every.
Yep. Sorry. Yeah, and you are back propagating the error. So meaning that what is happening here is that imagine that you get an output, and then that output is wrong, and you have visibility of the layer next to the output that with the weights that it had and the bias that it had. So what you are saying is this configuration of weights and this bias gave me this output, and it was wrong. So I need to start backpropagating this error to tweak and adjust those weights and biases that led me to this bad prediction. And then you do that layer per layer till the input layer, till the first layer. And then with this, what you are saying to the neural network is, so next time when you do another epoch, when you try to learn again, now you know that the error has been in every epoch is being minimized, because this is what we are doing when we said, I have a loss function that depends on the weights and the bias, and I'm going to optimize that loss function by finding the gradient of it. This is what we see usually in those explanations that involves differential equations and chain rule and all those things is happening here in this 1, 2, 3, 4, 5 lines of code. This is what is happening there. And the rest is just code that will tell me how am I doing during the process. And now I want to try the training loop, and I didn't instantiate the model. This is one of the things with Jupyter Notebook. Do you see that you can go on?
Have to run.
And you can go on, and now there is another error. Let's see.
You probably didn't do binary classifier.
Forward. It says this is missing the required forward function. So let me see, because we coded it. So this is another thing that I don't enjoy from Jupyter. You see it here.
Yes, that one.
Is bad indentation. So this is why it's saying that it doesn't have it. When I have but we have linters and unit testing and all of that. So now it works. This is the thing you learn when you start going to DevOps and software engineering.
Yeah.
There's a linter, there is a different code styles, and well, I don't want to go to that because it was traumatic.
I mean, it's nice to prototype, but sometimes you would like to, yeah. I agree. Yeah.
So this will take some time that probably we can use better. This training is relatively fast, I would say, because it's using the hardware of my Mac. And so here we see what's going on. So far, what we are doing is that we are training. And to the person that was asking about softmax, so I wanted to show that in this part in the prediction. So there is this part where the output will be a tensor with probabilities. And when I take the maximum and those probabilities, they add up to 1. And when I take the argmax of those ones, it will map it to the label that we define, 0 or 1. So this will take some time. So let me see if I can show you maybe do you agree I show you a finished?
Yeah, I mean, that's
or we can skip this part. I don't know how we are doing with the time?
We are a bit out of. I mean, we can do it 5 more minutes.
Okay,
10 more minutes.
So I will. Okay, 10 more minutes. So I will do this. So this is the reality of Jupyter. Jupyter Notebook is great for experimentation. But now what I wanted to show, and this I will speed up a little bit, is that when we want to push it to production, we move it, we refactor it. So we don't have Jupyter anymore. What we do
Now
is
we
that
need
we
to talk
can...
about classes, objects. We need to talk about real things.
Yeah, and we need to talk about, instead of prints, we have to do logging. So for example, here I am logging because probably someone can export the logs to another monitoring system and so on. So this, what I wanted to show is that this is the same script that we were working, but it should contain testing, and it doesn't have any of the visualization or the inspections that we're doing because you don't care about it anymore. You just want it when you are working on Jupyter Notebook. And so once we have this, and you see here that this repository has also another file that is called UI, which is the library that I was mentioning that is called Streamlit. That what I'm doing here is that now once I push this model to my CI/CD, this code to my CI/CD pipeline, it pulls the images, it trains the model, then it downloads the model and serves it in a UI. So let me show you real quick how this looks from this point of view. So now this is a repository with the main branch. So now let's assume that I go here to this. This is the same thing that we're working locally. So let's see that. Let's assume that I want to go to the training stage. Sorry, the training script. And I noticed that for whatever reason, the model is not good enough. So I said that probably it's because we are only training for, I don't know, 20 epochs. So let's say that I want to put it to 30. And you see that now, when I do this here, and I have it under version control, because this is on a repo with Git, version control management system, I can, and I'm doing this, please kids, don't do this at home. Don't commit directly to the main branch. This is for the demo purposes. I'm going to say that I increase epochs. And then I commit this to the main branch. When I commit this code and I go to the project, here you see the things that I was mentioning at the beginning that I found it pretty great when I discovered years ago this, is that now what is going on is that I can focus on the modeling or the data engineering or feature engineering, I mean. And whenever I want to deploy this as a product or for someone else to use, I can automate all of these steps. So what is happening here, this also will take some time, but so I will show you. Here we are building a front end. This could be another technology like React or something. We are using Streamlit. Here is a step where I am training the model with those new epochs that I define. And if all of these two stages are successful, then it will get into the deploy stage. That what it will do is that it will take the application in a container with the train model and will deploy it somewhere in any cloud that you want. So let me show you a pipeline that finished like this one. This is how this will look like at the end. So you see here that the training step happened. And we have it here that we see the same thing that we saw in our Jupyter notebook, but now it happened and I can see it thanks to the login that I was using. And now when we go to the other job, the last one, the one that is deployed, we see that this was in charge of doing communicating with the cloud provider, checking the credentials, and then it deployed the model to this URL, which is this service that with this URL that got automatically allocated that is called Miowski something. And this is how it looks. So you see here, I have the same service. And now the thing that we created in Jupyter Notebook by using a Streamlit, I can create a UI. And now I could send this to someone, to my friends, to my mom, and say, if you have pictures of my cat, if you want to try, now you can try it, and you don't have to show the Jupyter Notebook. So very simple application. I can click here and browse images. So you see that I'm having here the test data set. These are images that the model never got to see. They were not using during training. I'm going to choose this one. So I loaded, this is my cat, and then I can click on classify cat. And this is telling me that the classification is that it is indeed Miowski. This one is correct, and with this confidence level. So now let's try another image that is not Miowski. Maybe this cat. Then classify cat. And you see that it's telling me, oh wait, it was saying it says another gray cat, yeah. But gray cat as well, with this confidence. So as you see, what we did so far was that we were able to build a neural network that can take your own images, your own data set, and pictures of open source data set of cats, and you can create a classifier. So you can do this for dogs or for any image, but it just, I found it as a funny use case. So you see here that we went from the Jupyter Notebook to an application that it's automated by using CI/CD principles orchestrated in a CI/CD system such as GitLab. And the last thing that I will show is that, because I promised that I was going to talk about TensorFlow, is that, MLFlow, is that when we do this thing that you saw that I was doing, and we create code, the script in a Jupyter Notebook. Check this script, for example. What it's doing here is that I am wrapping the training. I am wrapping this model, the model, and this experiment. I'm creating an experiment in MLFlow, and I am by using this. GitLab has an integration with MLFlow. So when I, for example, in this function that is called register model, every experiment that I run in my code, or that I run using CI with this pipeline that is running, will be logged here into the model experiments. So you see that the last model that we trained an hour ago, the one before this live demo, I can see quickly here that if I were to collaborate with someone else and I said, let's use the best model, and in machine learning, the best is not necessarily the last one. In this case, this is the last one, but let's imagine that this one was the best. So what you could do is that, because this is a problem in machine learning, which is how can we reproduce experiments? So what this is allowing me to do is that I can come here where I have the logs, and I can see who was the person who triggered this job, who executed this training, and what are those artifacts that were generated. And by using MLFlow along with GitLab, you see here that I am logging two things. I have the requirements if you want to install it in your environment, and I have the model. So what this is doing is that it's making it easier for teams to say, okay, William, I want to try your model. So I say, okay, so Python 3.10, pip install requirements, and torch.load this model. And the likelihood that it will work will be higher than if you don't do this. So this is one way to help with that reproducibility of machine learning experiments and applications. And all of these things, they come from combining concepts from DevOps and machine learning. Because when we do all of these things now, the sky's the limit. I can create a release, and this can create release evidence. And if later I want to add security scanners, I can do it, and I can have a dependency list of all the packages that make up my application. And many regulated industries, they have to provide, this is more relevant than ever in the area of fairness and AI ethics. You have to be able to say, for example, in banking, I denied this loan application because of these reasons, and this was the model and the dependencies, the binaries and the code that create that. This is everything that created that model that led to that prediction. So for companies that they are highly regulated, having these tools, such as being able to track and have this traceability from, because if we go back to this, we can see who was the person who created it, when, how, and what was generated. So this is pretty helpful too, not only for collaboration, but also for auditing purposes.
Replication, nice. No, that's amazing. I mean, I love it. One of the questions that we had is they're asking if the code will be available.
Yeah, sure. I will share it. I'll send it to you. You send it to everyone. And the slides.
once we posted in the recording, we'll put all the links to all the tools that you used, which are all open source. So everything that you use, it's open source. Nothing is proprietary. So people can be relaxed that we are using all open source, and they can easily replicate your use case.
Yep.
Probably not with your cat images, because that's private.
Yeah.
But yes, that's
with their cat or dog images or hedgehog or hamsters.
or whatever. But moving that, for instance, to a business use case can be, if you like to identify, I don't know, a truck or something that it's not. You would like to identify a car, or would like to identify something similar, your car, or a person, or whatever. This is mainly also the goal of all of this. Of course, if you like to build something for your pet, it's great, but that's mainly the idea behind that. It's that. So, I think it's great. I think it was great. We did it on time, so that was great. I don't know if you'd like to add something more before we wrap up.
Nope, I wanted to. That's all that I have prepared to show you end to end, and I think I covered the main topics that I wanted to cover with all the tooling, the problem that I wanted to solve, how I solve it. We did it together. How you can operationalize it, automate it, and deploy it and use it. So yeah.
That's amazing. That's amazing. All right. I mean, we had some questions during this session. So if you have any other questions or anything that you would like to know, just that will be posted on YouTube and LinkedIn. So feel free to add any comments that William will answer for sure. So no, just joking. So all right. Thanks so much for you, William. We really appreciate it. We really enjoyed. I mean, I think that was great. It was awesome. So I really enjoyed the time. So thank you so much for being part of this. And for the audience, we'll be doing the same similar session probably next month. Our idea is to do it monthly. So thank you so much for your time, and see you next time. Thank you so much.